Let's look at a simple example of the application of our kinematic assumptions. So suppose I have a beam of length L, depth h, and width b, and so it's got a rectangular cross-section, and I'm given that the deflection in the y direction, so the vertical motion here, v of x, is given to me as a cubic polynomial. So a and b are just given constants. X is the axial coordinate, L is the length of the beam, and let's determine what the rotation of the cross sections is and what the bending strains are as a function of both x and y in the beam. So to find the rotation, I make note of the fact that the rotation is equal to the slope of the deflection curve, and so all I have to do is take one derivative of v with respect to x, and that gives me the expression for the rotation field of the beam. So that's relatively straightforward. So anytime you know the motion, you know the rotation already. If I want to get the bending strains, I'm going to use the relationship that epsilon is equal to minus kappa y, so I need to find the curvature first. So the curvature, though, from our assumptions is that the curvature is the rate of change of the rotation field, which is the same thing as the second derivative of the deflection field. So I just need to take two derivatives of v. So I take one more derivative of the expression I've already determined for the rotation, and that gives me the expression for the curvature field. And now all I have to do is multiply that minus y, and that's going to give me then the expression for the strain field. So the strain field in this case is a function of both x and y. So y is the coordinate on the cross section, and x is the coordinate along the length of the beam. So I have it's changing linearly as I move along the length of the beam, and it's also changing linearly on every cross section.